All right, hello geometry students, happy Friday. Today we are starting chapter 10, which is circles, and today we're going to do our day 1 packet of circles. So circles are any set of all points on a plane that are equal distance from a given point, which we call the center. Circles are named by whatever center they have, so in this case the center is C, so that is circle C. If you have a highlighter, now would be a great time to get it because we're going to highlight some of these vocabulary terms. Different parts of a circle are listed here. First, we have the radius. The radius is any segment with the end point on the center and the other end point on the circle. So CF is an example of the radius in this circle. Other radii would be CD or CE. Both of those, all three of those are examples of the radius. Has to start at the center and go to the outside. The second term we're going to talk about is a chord. A chord has both endpoints on the circle, meaning that you have A and B. This is considered a chord. Does not have to go through the center, but it can because DE is also a chord. But DE, more specifically, because it goes through the center, is considered a diameter. A diameter passes through the center and is made up of collinear radii, so two radii that are next to each other. So this here is the diameter. Pretty confident that you have seen all these terms before as they are, I've taught these to my middle schoolers, so I'm sure you've seen them in middle school or even before that. We're going to talk about two specific types of intersections that go through a circle or touch a circle. The first is called the secant. A secant is any line that intersects at exactly 2 points on the circle. So here we have one intersection, two intersections, so that would be considered a secant. And here we have one intersection, two intersections, so that would be considered a secant. We're going to talk more about secants next class period, but that is just an introduction to secants. The second type of intersection of a circle is what we call a tangent. We've heard that word before. A tangent specifically is any line that intersects a circle in exactly 1 point. So here is our point of tangency, and it only touches at 1 point. So it could be a line, it could be a line segment, or it could be a ray, but it only touches your circle at 1 point. Let's go ahead and turn the page after you get all of those highlighted. So specifically, the tangent was what we're going to focus on today. A tangent and a radius will always intersect at a perpendicular angle. So any tangent is always going to be perpendicular to the radius of a circle. So if I have number 1 here, OB, because AC is a tangent, OB, the radius has to be perpendicular. Same with OE, it has to be perpendicular to DF, as well as OH has to be perpendicular to GI. So if we're looking at, if we were to make a note of that, we would say that all radii, a radius is always tangent to, a radius is always perpendicular to the tangent. So go ahead and get that written down. How do we use that in a circle and triangles? So you'll see this come up a lot where you'll have a tangent that forms the perpendicular angle and another line that forms a triangle, and what happens is it becomes a right triangle. So in this case, AB is perpendicular to BC, therefore AB must be a tangent, because of that perpendicular 90-degree angle. So that is given to us. But it won't always be given to us. Sometimes we'll have a problem like number 3 here. I don't see any 90-degree angle. I see a circle. I see AB touches the circle, but I don't know if it goes through or if it's just barely touching it. And I really need to find out, is this a 90-degree angle? So is there any way that you can show that that's a 90-degree angle? Well, since it's a triangle and I know 3 sides, I could use A, B, and C and use the Pythagorean theorem. And I would get a squared plus 6 squared should equal 10 squared if that indeed is a right triangle. And it does. So AB is a tangent of BC because of that right triangle. Why don't you guys try number 4 on your own? Pause this video real fast and go ahead and try number 4 on your own. $52 does not equal 81, so this is not tangent. It would have to be a right triangle in order for it to be tangent. All right, guys, so let's go ahead and have you try 5 and 6 on your own. 5 here, this you try 5, and then turn the page, and this would be considered 6. So try those next 2 problems on your own. So I got 8 for this problem here and 10 for number 5. Any questions? Let me know, and we will go over this when I return on Tuesday. So you should set up the Pythagorean theorems accordingly. Remember, this is your 90-degree angle, and this is your 90-degree angle. All right, math students, let's go ahead and try number 15. Same idea, but now we have some unknowns, specifically the radius. So for this, I really want to focus on using the Pythagorean theorem. And I'm going to say a leg, and the hypotenuse, because I already have A, B, C, and I don't want to confuse you. So in this case, it looks like my 2 legs are 4 and R. So I'm going to put a 4 here and an R here. But then what about this hypotenuse? How do we write that out as a side length? I'm going to write it out as 2 plus R. So I'm going to use 4 squared plus R squared is going to be all of 2 plus R quantity squared. And this is where your warm-up comes into play. 2 plus R quantity squared is just 2 plus R times 2 plus R. So you're going to use the FOIL method to work that out. And you get 4 plus 4R plus R squared. And then you would subtract out your R squared, and what happens is they cancel out on both sides. And so that's fantastic because now I don't have to worry about quadratic equation. I'm going to subtract 4 from both sides to get 12. And then I divide out by the 4, and my radius in this case is 3. I want you to use that same method that we just did to try the next one on your own. And you should get that r equals 5. So you're going to have a few more of those problems on your homework later on in this packet. When you're ready, go ahead and turn the page, and we're going to take a look at tangents. So there's two types of tangents here. We have common tangents, internal, and common tangents, external. When we have an internal tangent, what happens is the tangent line is between the two circles. So the tangent line or the circles are on opposite sides of the line. Whereas if you're looking for external, then the circles are on the same side of the tangent. And so you have a couple different, you can have both. So here we have two internal tangents, whereas we have two external tangents on the outside. Here we have two external tangents on the outside, but then only one internal tangent. Here we have no internal tangents and only two external tangents. And here we only have one external tangent and then no tangents. So those are just the two different kinds of tangents that you can see when you have common tangents on two different circles. So for number 7, we would have two external tangents because they do not go in between the two triangles. So we have two external tangents, or two external common tangents. And then here, we're going to have two external, I'll draw a better straight line there, and one here. And then we have the two internal that cross in between. So we have a total of 4 tangents, 2 internal and 2 external. When you have external tangents, they form 2 congruent segments. So as long as they are tangents from the same point, they will be congruent. So AB has to be congruent to CB because they're both tangent to circle D and they're coming off of point B. So since I have these 2 tangents here and they're both tangent from the same point B to the same circle D, we could make the statement that x plus 15 equals 2x minus 5. And then we go ahead and solve that equation to get x equals 20. So why don't you guys try that next one on your own? Those 2 tangents are going to be equal, so the equation you're going to have is 3x minus 6 equals x plus 10. Go ahead and solve that for me. And you should get x equals 8. Subtract 1x, add 6, then divide by 2. So we're going to use the same concept here on this next page when we're talking about circumscribed polygons. If a circle and a polygon are circumscribed, then each of the sides meets the circle at exactly 1 point on each side. So every single side of the polygon has 1 tangent to the circle, but not overlapping it or intersecting it. So here, do you notice how the triangle is outside the circle? Or the circle is outside the triangle? That's not circumscribed. Here, we have this big empty space here. That's not circumscribed. And on this last one, the circle doesn't even touch the polygon. So none of those are circumscribed. It touches at exactly 1 point. So taking that last concept of these parts being congruent, I can make the statement that this left side is 4, so the right side also has to be 4. Down here, if one tangent is 9, the tangent on the other side is also 9. And then this last one to G, if this is 13, this last one is 13. So in order to find the perimeter, we would take 4 plus 4, 13 plus 13, and 9 plus 9, which is 8 plus 26 plus 18, which is 52. All right, math students, finish up with the rest of the notes on Google Classroom. There's one more example. I'm going to have you try this next one on your own. And then the rest of the packet is yours to finish for homework. Have a great day.